So, okay, it's now recording.
I want to thank last week's speaker Ken Owens for some one-dimensional fusion that we have to
recording
on 3 dimensions, and tell you that next week we have a wildlife professor, Daniel Martin, is going to talk about
Don't touch it. Here we go. Just a little bit this way, so mostly it's on the
Bayesian
slide.
analysis.
No, you are not including Jeff right now.
It's okay. He's going to be more here, where the computer is. And then you can still see the board.
Oh, because it's being recorded, it may not stop until the battery runs out. We are okay, I think. Perfect.
Martin Flashman is in the house. Martin is my longtime colleague here at Humboldt State University. He was here even before I got here. It was like now. It's starting to feel like I've been for a long time. Martin has 2 doctoral degrees, only one of which is in mathematics. The other is not in philosophy, but it may as well be. It's in law. And so, don't argue with the guy. No, actually, Martin relishes arguing, so please, feel free to jump in. I see that one of the people that he likes to do philosophical work with is someone else. Anyway, Martin has been thinking about the role of philosophy in proof probably on a long time, longer than I've been at Humboldt State, which, as I mentioned, is a long time. Marty, when did you get to Humboldt? 81. Okay, so he goes back a ways. And when were you starting to think about the role of philosophy in proofs?
That's a lot before that.
A lot before that.
That's like 1967.
So this will today be a treat because it is the result of years of thought by a guy with a big brain. Please welcome Martin.
Yeah, thank you, Jeff. It brought to mind that question, so when did I start thinking about this? And it wasn't Brandeis when I took a...
Matt 45, be sure to get on the switch list.
Go ahead, interrupt me.
Sorry.
When I was an undergraduate at Brandeis, I took a seminar as a senior. It was a graduate level seminar in the philosophy of logic, taught by John Heinrich, a pretty famous physician, and also was Secretary of Trusts. So I want to talk about the role of philosophy in proofs, and there's a slide up in here. Oh, I know. Take that off. I gotta put this back on the So I've got some questions to ask you in preparation before we get started. The first one is, so how many of you have actually taken a course or are currently taking a course on proofs from the math department? So that's math 240. Okay, so keep up so we can see how many people we need to avoid.
You're just talking about students, right?
Okay, what?
You're just talking about students.
Yeah, I'm talking about students, not the instructors. The instructors know themselves, and I know who they are. Next. Why is it like that? Oh, I'm going backwards. Why is it going backwards? Never get started. Okay, that was good. I'll get it started again, okay? Ding, 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 ding. Think. Forget that question. Next one. So, how many of you have taught a logic course? Not taken one. Taught a logic course with 2 tables and used Venn diagrams for quantification data. So, taught. These are the people. So, I got you guys later, see? We've got a bunch of them like that. And the students, of course, have already had that experience. If you're taking the Introduction to Math 5 at 240, that's sort of the way things are done there. They do some truth tables, and then they occasionally do some Venn diagrams to explain something about quantifiers. So, this is wherever. How many of you have discussed philosophy in these math courses? No, not too many. Okay, so this is new for some of you. And so we're going to start off with what I think is a really valuable tool for thinking about problem solving. George Koya isolated what he considered 4 phases of problem solving. It's working now. First part is understand the problem. Second is see connections to devise a plan. Third is execute or carry out. Execute, we don't want to be executing people anymore. So we just carry out the plans. And then fourth, look back and reflect at the process and the results. So, the question is, what role can philosophy play in problem solving and proof, which is perhaps maybe step 1, understanding the problem, but also might be in step 4, looking back and reflecting on what happened. So a little bit about mathematics and proof. Mathematical proof is not the same as a demonstration involving just truth tables and syntax of quantification. It's more than that. When you do a proof in mathematics, you have to get involved in the actual content, in the context in which those statements are being made, whether they're conditional statements or quantified statements. They're not just about language. They're about specific language which is tied to a specific context that somehow or other is identified as mathematical. So, here's some philosophical questions. First one. What is the nature of the objects in a mathematical discourse? What are we talking about when we talk about mathematics? Well, when we think about the nature of those objects, philosophers say, well, that's a part of the philosophy that's referred to as ontology, the nature of the being that we're talking about. We'll get a little bit more on that. Second question is, what's the nature of the mathematical structures that are being discussed? Like we're talking about vector spaces, or groups, or fields, or continuous functions, and a whole collection of functions. So that's also a little bit about ontology, because we want to know what's the nature of those objects that we're talking about in the structural format. And then finally, we get this question about what's the nature of mathematical knowledge? When do we actually know something, and how do we know it? How do we come to know perhaps the truth of things? And that, in philosophy, is generally characterized as a part of epistemology, although some people would put it in metaphysics. But metaphysics can be really much too broad a topic. So when we talk about how we come to know things, I'll say that's an epistemological question. And when we ask what's the nature of these things, I'll say that's an ontological question. Okay, so here's from Wikipedia, a quick through what ontology is according to Wikipedia, and a very great authority source. These things are actually, unlike mathematics, where there's a whole group of people who, when somebody goes up in the Wikipedia for mathematics, there's a whole group of mathematicians who go in and see whether they think it's right. That's not going on in philosophy. So Wikipedia is a little bit weaker in philosophy as a resource. The Stanford philosophy resource is probably better, but here's a quick on what ontology is. Okay? So it's a philosophical study of the nature of being, becoming, existence, and what's the nature of reality, and categories of being. Okay? So it answers questions about what entities exist and what can be said to exist, and how do you know they exist. And I like getting to epistemology a little bit. And there's sometimes there's a relationship, a hierarchy of these beings. So beings depend on other beings, depend on other beings. Epistemologies. Another quickie from Wikipedia. I hope it's quick. So that's a branch that deals with the scope and basic nature of knowledge, and also how we come to know things. What is knowledge? How can knowledge be acquired? You buy it at the store. You go to Wikipedia. Now, what's the quality of your source? Do you depend on authority, or do you actually have some personal experience in that knowledge? Or do you just rely on me telling you something? Or if you don't rely on me, maybe Jeff. Okay. And to what extent can knowledge be pertinent to any given subject or entity? Okay. The relevance. And finally, how does the nature of knowledge relate to the connected notions such as truth and belief and justification? So they're all meshed up together, and it's a difficult thing sometimes to separate knowledge from beliefs, especially, and the truth, and who knows what that is. All right, so I want to talk a little bit before we get started about this. There's a thing called ontological commitment. All right, now that topic was actually brought to the front in the study of philosophy by a guy named Wilhelm Quine, who wrote a couple of great logic books. But he was a philosopher at Harvard, and he was a good friend of my teacher, John Heine. And I actually saw him. He rarely gave talks, but he actually came to Brandeis once and gave a talk about the nature of questions. And so, what is ontological commitment? Well, in philosophy, you say that a theory has an ontological commitment, or is ontologically committed to an object, only if that object appears in all the ontologies of that theory. So what does that mean? Well, that means that this theory isn't going to work unless we believe that this object exists, or unless we accept this object exists, or if it's a part of our major fundamental claims that this type of object that has some kind of existence that we can deal with. Now, the history of ontology is kind of, in mathematics, goes back pretty far, and we'll see that in a little bit. But we can talk about geometry. So, is geometry, I'm using OC, it's not OCD. It's OC. I don't want to be too compulsive about this, but OC stands for ontological commitment. And so the question could be, is geometry ontologically committed to some nature of points? That there's things called points and they have some being to them that is fundamental. And if you think about geometry and anything you've ever studied about geometry, then you always talk about points. Anybody who wants to talk about points, about geometry, is going to talk about points. So what do we mean by points? Well, there's a long history of that. And one could go back to the great Plato and Aristotle and Euclid as the three great ancient Greeks at least, who were in some sense dealing with or wanted to talk about philosophy and geometry. Now, Euclid, you say, well, Euclid didn't have any philosophy. It was a textbook. He just collected everything and put it all together. But what he was talking about is not clear that he didn't have some ontological commitment to points. And in fact, we might think that Euclid was either a Platonist, whatever that might mean, which means that the objects that he's talking about are in some kind of reality that's not necessarily the reality of physical reality, but some reality alternative to physical reality. Or it could be an Aristotelian who's talking about, well, what I've really done is collected all the properties of the reality that I have encountered, and I put them together and use this phrase to characterize these things, but they really are describing things that are real. So you could be an Aristotelian collecting knowledge and putting it forward in some kind of summary form, or you could be Platonic and thinking that this is really idealized what I have encountered in the real world, but it's not the real world, it's the idealization of that. And it's not ideas, it's idealization. We don't want to think that it's all in my head. This lives outside of me, but it has some kind of reality, but it's not the same as a physical table. So we have the property of tables, we have tables, podiums, but then we have the property. We can talk about tables and podiums without actually having a physical one in our presence, and so we can have these things called points, but there might not be a point that I can actually point to. So the question of the ontology of the geometry, is it committed to points? Well, I would say that Euclid, whatever his ontology is, and he doesn't make it explicit, is definitely committed to something that these points have some sort of being to them. They're not fictions. Later on in the history of mathematics, and we go way back, we're coming up to the beginning of the 20th century, we get a philosopher, a mathematician named David Hilbert. And for David Hilbert, the nature of these points is really a lot more flexible, and it's really just a word that can be filled in with anything. Hilbert has very little ontological commitment to the word point. The only way he gets his meaning for points is to put it in a context in which he's described all the properties of points, and then he knows what a point is, but it doesn't have any property outside of the description of the whole structure. So it fits, it is ontologically committed to the point only in a large context that somehow has been accepted for discourse. So it's a very different kind of belief and treatment of the word point than what Euclid, Aristotle, and Plato might have used. Well, what about an arithmetic? What about numbers? Well, there's the same kind of stuff going on in numbers, and we'll look at maybe at that. Euclid talks about numbers, and Euclid's numbers are not the same as the numbers that are talked about in the late 19th, early 20th century by Peano and Frege. They're talking about different kinds of things where they're much more interested in the structures, like Hilbert was, that characterize what we want to call numbers. And that's not the only numbers. There are other numbers, like real numbers, things that we study in calculus, numbers that are, or imaginary numbers, which were not even allowed to be numbers until, after the 18th, 19th century, they come into, getting to be allowed into the world of numbers. Before that, they were some weird gadget that we might talk about as fictions, like unicorns. And so it's really, the numbers are no more clear in their ontology, perhaps, than the points. And then, in mathematics as a whole, in current mathematics, people, beginning in 1940 and before that, in grammar school now, or in high school for sure, somebody wants to talk about sets and say that's a part of mathematics to talk about sets of numbers, sets of points. They're just sets, whatever sets might be, whatever you like. And so, is there an ontological commitment in mathematics as a whole to have objects called sets? And that comes to the front in the late 19th, early 20th century with work by Cantor, who was talking about problems with describing sets and finding out that sets are not all that we thought they were. And then there's all kinds of paradoxes that appear in sets in terms of not just sets themselves, but paradoxes like being able to have a set that wasn't measurable. Or being able to have a set which you could cut into two pieces, and the, quote, measure of that one set could be cut into two separate pieces, and they would have the same measure as the one set. So you could make $2 out of $1. You're really making money that way. So, so there's a whole problem with what our commitment is to sets. And in the 20th century, a whole development of mathematics called category theory, in which the objects, sets are just one kind of category, and then maybe you're not so committed to sets anymore. Maybe you're committed to categories, whatever that might be. But most people, conventional mathematicians, have a pretty strong commitment to having something called sets. But there are problems with that, and about what characterizes a set, what are the axioms for sets. And those problems in this century, 21st century, have led to some really interesting developments where things that we thought we knew about sets have turned out to be problematic, and we really don't know what we're talking about when we talk about sets anymore. Weird thing. So I'm going to talk in the time remaining, as time permits, about 3 of 6 statements that I have here. And these are statements. This work is work that I've been doing. Recently, I gave it. Last summer, I gave a talk on this subject at the Summer Math Fest, and so there's a compendium of essays and articles about philosophy of math, and so I've been asked to write an article based on this for that publication, and I'm working on it, and hopefully it'll get done by the time when the editors want to have it done. But if not, I'm having a lot of fun talking about it anyhow. And I've given this talk in a couple other places. I want to say that this is a very good audience today, and unfortunately, you don't match. I actually had an audience this fall at Folsom Lake College, community college.
Yeah.
Okay. There were about 50 people in that audience. 50 students at full supply college. So we're doing pretty close to that, but it was standing room only. So there's a lot of interest in mathematics outside of Humboldt County. All right. Surprised. I know, you didn't think so. So here's the propositions. The first one I might want to talk about is Proposition 1, Book 1 of Euclid. Now, Euclid is, for thousands of years, not thousands, well, almost thousands of years, many hundreds of years, was considered the Bible of mathematics. It has everything that you ought to know, and everybody who wanted to be a mathematician read Euclid. And the beauty of Euclid was always pointed to, well, Euclid's got it all down there. It's the model for writing proofs, it's the model for developing everything. It's the model for doing physics, it's the model for all science, it's a model for the Constitution of the United States, it's a model for everything, okay? Or the Declaration of Independence, at least. You know, it's going to connect everything. You're going to have some fundamental principles. These things we hold to be true, that all men are created equal, blah, blah, blah. That's all based on Jefferson's reading of Euclid. Another piece of mathematics. So, Book 1, Proposition 1 is a very simple thing, and you say, well, why is this there? Well, there's a whole structure in Euclid, and this is the fundamental proposition of practically all of Euclid. And the proposition is so simple: to construct an equilateral triangle on a given straight line segment. That's it. That's Proposition 1. So we're going to talk about that and its proof. Second one, another one from Book 9, Proposition 20. Euclid does everything. So Euclid's doing geometry at the beginning, but by the time he's in Book 9, he's well into numbers. And so this is a proposition from Euclid's number theory. Prime numbers are more than any assigned multitude of prime numbers. What does that mean? That means that if you collect a bunch of multitude, you get that word set. If you collect a set, a multitude of prime numbers, you get them all together. You know, get 3, get 5, get 13. Just collect as many as you like. If you think you can get them all together, you're wrong. Whenever you think you've got them all collected in a finite multitude, any assigned multitude, you're missing somebody. They got left out of the party. There's always somebody else who wants to come to the party. That's Proposition 20. Now, there's a theorem I'm not going to talk about, but it's one I like to talk about philosophically, and that's a theorem that people sometimes attribute to Pythagoras that says that the square root of 2 is not a rational number. Well, I'm not going to go deeply into that, but there's a first question before we say what kind of number it is. Is it a number? I mean, why should we talk about something? It could be a unicorn, in which case I'm sure unicorns are not rational numbers. All right? So, when you say the square root of 2 is not a rational number, what are you talking about there? How does that get to be a number? Because the people that usually refer to the square root of 2 when they say, well, what is the square root of 2? They'll say, oh, well, you take a square with unit length, and the diagonal of that square will have length, square root of 2. So, the square root of 2 must be a number. So that's already making a commitment to what numbers are. It's saying numbers, for that person at least, are things that are used to measure things. All right? And if I have a length, I should be able to measure it, and somehow or other I believe that this length, the diagonal of a unit square, must have a length, and that length must be a number, and that length I think is a number which when I square gives me 2. All right? There's a whole bunch of philosophy going on in there. Before we even get to say, well, you know, there is such a number, and then to say, oh, but you know, it's not a rational number. We have to know what rational numbers are as well. So there's a whole bunch of stuff going on there. We're not going to talk about that. Okay, another one, anymore. Here's a couple that are due to Cantor. So these are, the first one is that if you take all the rational numbers, remember the prime numbers, we can't get them all into a set. So the rational numbers also can't be gotten into any finite set, but you can get a correspondence, the equinumerous, with a set of natural numbers. Natural numbers. Well, Jeff and I can have an argument about what's a natural number because Jeff doesn't believe 0 is a natural number, but I do.
Oh, no.
Oh, you're in with me now?
Well, I go with the book I choose for Math 240.
Okay.
I let the book decide.
There's not much ontological commitment with this guy. Okay, don't need to pick on you that much, just a little. So that's a big result of Cantor, and it has a way to systematically count those things. how do we show something's equinumerous for something? You have to have some way to characterize that correspondence between one collection of numbers and another thing. You're getting close to set theory. You're talking about, well, what do you mean by equinumerous? You're talking about functions. Already we're getting in the commitment to set theory and to functions, all right, in Cantor. He has a second one. This is the bad one. The real numbers, or points on a line segment, if you don't want to think about real numbers and you just want to think about the geometry. The points on the line segment, any particular line segment in Euclidean geometry, are infinite, but not equinumerous with the rational numbers, or the natural numbers. So the first one's the good one. You can count up all the rational ones. We're going to assign a counting number to each one of them. But when we get to the real numbers, or even just the points on a line segment, we got a big trouble. Now it's interesting because Cantor's demonstration of this, his first demonstration was geometric. So he was talking about a line segment the same way that Euclid in Proposition 1 is talking about a line segment. So it's interesting that with all that time between them, they still want to talk about a line segment. And they still want to talk about points on a line segment, and we'll see about that later. And the last one of these, which if I have time I'll talk about, is Russell's a theorem that's due to Russell, but you might not even call this a theorem. It's talking about a set. So we're talking about, okay, we're going to have some commitment to sets, and if you're going to have things that are sets, you want to be able to talk about something that's not a set. So you can distinguish: is everything a set, or is there something that's not a set? So one of the big results that Russell put forward, and actually this was a counterexample to some stuff that was going on, because there was a book that just came out that had everything, was building all of logic and had sets, and said all mathematics is going to work this way out of this collection of. What?
The third has to be an on.
Not an element of S, no. So look here, all those sets with a set, all those things S, which you might think about sets, where S is not an element of the set S. Not an element of S. We have a set, I can say, okay, you're an element of the set of people in this room, and somebody outside the room is not.
So it's unrelated to the R in front.
R is the name of the set.
Okay.
This set is named R. Well, but this set is not a set.
The thing you're calling R.
Is S
The thing what R describes is not a set.
okay.
It looks like what we call a set, but it's not a set. And that's what Russell demonstrates. And this is sometimes called the Russell set, and the fact that it's not a set is sometimes referred to as Russell's paradox, because people think it should be a set. But if you just want to say, hey, it's not a set, there's no paradox. It just looks like a set. It's like, I look like I'm the main speaker here, but actually Jeff is. No. All right, so let's look at Proposition 1, book 1. And this is the figure that's on the announcement of the talk here. So I wanted you to see that picture. And the proposition is to construct an equilateral triangle on a given finite straight line. So this proof is, what I'm giving you here is, I'm actually going to move to another page here. We'll do this. So this proof, it's a little bit hard to read, it's small, but we'll see how it works. I'll just read it to you. So in this proof, the object is to construct an equilateral triangle on a given finite straight line. And so this is actually taken from this guy named, I can't remember, it's David Joyce, I think his name is. He has a website we'll look at in a